Hey, students and teachers, welcome back. This is part 2 of our experimental design lesson. This can be found in Module 1, Lesson 4 of the booklet that we use in our class. If you're following along using this textbook, you can find it in sections 4.2 and 4.3. And if you're just trying to casually explore AP Classroom for some similar problems, you'll see those problems in topics 3.5 to 3.7. Let's get started. So you might remember the caffeinated cola experiment we did, where we had 20 people randomly assigned to a caffeinated cola and the other 20 to a non-caffeinated cola. And of course, they didn't know they were double-blind experiments. So we could compare the results. Here's some data from that. So we have the 8 change in pulse rates measured for the caffeinated, which had a mean change of 3.2, and a non-caffeinated, which had a mean change of 2.0. So as you can see, there was an increase in both of those, and that's because of the placebo effect, or maybe just sugar in the cola that might affect that. So we want to see, is that difference, which is 1.2, statistically significant? Boy, I have a hard time saying that word. So we're going to do a little simulation to find out. You can follow along with the simulation by going to bit.ly/CAFSIM part 1, uppercase C, uppercase S, uppercase P, and it'll pull you up a Google spreadsheet we can use. Go ahead and make a copy of that so that way you can edit things as you need to. So actually, let me pause this for a minute. So you'll make a copy of this spreadsheet, and the spreadsheet has the data here for caffeine and non-caffeine, and then just all of them stacked together. So you'll see these top 10 are column A, and these bottom 10 are column B. What we're going to do is just completely randomize it all, and just assume that no change is going to happen with drinking caffeine versus non-caffeinated soda. So we're going to just assume there is no difference. So we'll do some simulations based off that information. What we're going to do is we're going to just take the numbers here. We're going to verify first that these averages are what they say they are. So notice that if I highlight these numbers, that is an average of 3.2. If I highlight these numbers, it should be an average of 2.0, and it is. So now what we're going to do is we're going to highlight these 20 stack numbers, and we're going to randomize them. We'll do that by going to data. We're going to go to randomize range. Now notice that the numbers are in a random order. And what we'll do is we'll just take the top 10, highlight them. You'll see an average of 3.3. And then you'll take the bottom 10, and you'll see an average of 1.9 in my case. So I would say 3.3 minus 1.9. And of course, I get a difference of 1.4. And that's one simulated difference. You can do the same thing with a bunch. If you're in a classroom, do maybe 5 or 6 of these, combine them with all your students, you can get a really big set of data. And you can collaborate that by putting them into a single group, collaborative, one quantitative variable group in Steplet. I'm going to go ahead and randomize it again. Go ahead and do the same thing. So 2.4 and 2.8. So I'll just go ahead and do that here. And eventually you'll get a whole bunch of numbers here that you can plot on a dot plot and look at what that simulation would look like. For the sake of time, I will show you my already pre-made one done. All right, here's what it looks like here. Notice that I have a lot of dots centered around 0, which makes sense because we're assuming that there is no mean difference in the change of pulse rates. So now I want to look at my difference, 1.2. Based on my dot plot, and you look at where 1.2 is. So 1.2 is going to be right around here. Look at all these data points there and above. Could that easily happen by random chance? That basically tells us how to answer this question. So it all comes down to the word statistically significant. When an observed difference in responses between the groups in an experiment is so large that it is unlikely to be explained by chance variation in the random assignment. That means the results would be statistically significant. Now, if you look at my data here, how many of those dots are at 1.2 or more? Go ahead and pause the video and count them. Turns out there are 22 of them. Now, 22 out of 100, I have 100 points on here. It's a pretty big number, right? It's very easy to say that, hey, this could have been easily explained by random chance, okay? If I mix them all up, the chance of me getting a difference of 1.2 or greater just by random chance alone to the random assignment is pretty high, 22%. So that's not statistically significant. What we're looking for on there is numbers that are less than 5%. That's generally the standard for looking for those percentages. So if my difference was like 2.5%, notice that there's only 3 dots that are above 2.5%. It's only 3 out of 100, which is 3%. Then I would have statistically significant results by this 5% threshold. In the case of my data, I do not. So I can't certainly say that drinking the caffeinated cola caused the increase in pulse rates based on this experiment. Now, later in the lesson, we'll see a better designed experiment that can maybe produce statistically significant results. So stay tuned for that. Example 1. Is talking on a cell phone while driving more distracting than talking to a passenger? David Strayer and his colleagues at the University of Utah designed an experiment to help answer this question. They used 49 undergraduate students as subjects. The researchers randomly assigned half of the subjects to drive in a simulator while talking on a cell phone. The other half were to drive in the simulator while talking to a passenger. One response variable is whether or not the driver stopped at a rest area that was specified by researchers before the simulation started. The table at the right shows the results. We want to calculate the difference between passenger minus cell phone and the proportion of students who stopped at the rest area for the two groups. So it looks like we have stopped at the rest area. We got two groups, cell phone and passenger, and that proportion would be 12 out of 24 and 21 out of 24. So we're going to do passenger minus cell phone, so we're going to do the bigger one minus the smaller one in this case. So that's going to look like this. It's going to have just 0.875 is what these divide to. 0.5, 12 out of 24. Those subtract to 0.375. All right, it's a pretty big number. Now let's look at the next component of that. So the blue dot here is a simulated dot representing one of those simulated differences similar to what we did in the activity prior to. Let's read this description up here. 100 trials of a simulation were performed to see what differences in proportions would occur due only to chance variation in the random assignment, assuming that the type of distraction did not affect whether a subject stopped at the rest area. That is, 33 stoppers and 15 non-stoppers were randomly assigned to two groups of 24. Pause for a moment. Why 33 stoppers and 15 non-stoppers? Why was it important to have different amounts there? I'll let you think about that. Kind of requires going back over here thinking about it. In our study, we found that there were 33 that stopped and 15 that did not stop. So in order to have an accurate simulation, we want to use similar numbers to what we did in our two-way table here. So that's the reason why those numbers exist. All right, back to the question. So the dot plot displays the results of the simulation. This is one blue dot up here with a difference of 0.125. What does that mean in this problem? So what that means is one simulated random assignment resulted in a difference in proportions of students who stopped of 0.125. So one simulated random assignment. There's a whole bunch of them in here, but this blue dot represents one of them. Next part. Using these results to determine if the difference in proportions is statistically significant. Explain your reasoning. Now let's look at how many of these dots over here or more were greater than our difference from our two-way table. So if you remember from our table, we had a difference from those two proportions of 0.375. It's a pretty big difference, right? Now look at the simulation and look at where 0.3 is. We don't have any numbers out here that are 0.375 or more, okay? So that proportion from our simulation here is just 0, okay? Now, the likelihood of that happening by random chance alone is not 0, but it's very, very, very close to 0. So because a difference is greater of 0.375 or greater never occurred in this simulation, 0, the difference is statistically significant. In other words, it's extremely unlikely to get a difference this big simply due to chance variation in the random assignment. It's a very wordy way of saying it's very unlikely for this to happen by chance alone. So I'm going to say that this is statistically significant. So that leads us to going back to experiments and talking about the language of how to set up a well-designed experiment so we can show statistical significance. Let's consider the following scenario. A university school of agriculture has been developing a new variety of blackberry plant that is designed to have a greater yield than the current blackberry plant. To put the new variety to the test, agricultural students perform an experiment using two different fields. The smaller field is more fertile and has space for 4 plants. The larger field is less fertile and has space for 6 plants. In this context, the treatments are the new variety and current variety plants, and the experimental units are the 10 available spaces where the blackberries will be planted. Because of the differences in fertility between the two fields, the blackberry yields are likely to be more variable than if all the plants were grown in equally fertile soil. This additional variability may make it difficult to detect a difference in the average yield of the two varieties. To account for this source of variability, we form 2 blocks of experimental units. One block contains the 6 less fertile spaces, and the other block contains the 4 more fertile spaces. Now, you remember back in surveying where we try to group people by similar characteristics, known as a stratified random sample? Well, in experiments, we call this blocking. This is not a theater thing, so you theater nerds, this is just blocking by groups of similar like-minded subjects. So in our case here, we have fertile soil spaces and maybe not so fertile soil spaces. And notice that they're not necessarily the same. We're dealing with what we have, right? So if there happen to be 4 fertile soil spaces here, then we'll put those together. And the less ones are going to go in their own block. Now what happens is we do a little mini completely randomized design for each one. So think about like this right here. This top one is going to be a completely randomized design just for the more fertile ones. And you can notice that we're going to randomly assign them to the new and current treatment. And the same thing for the less fertile ones. We're going to randomly assign those 6 to the new and the current treatment and compare the yields within each block. So you have like 2 little small, completely randomized designs. That's important because we want to account for the variability that maybe occurs naturally from the types of soil that exist. So spread them out, space them out, do your own little experiments on them. And then at the end, you can determine if the results are statistically significant by comparing everything. So this is how it works in a problem like this. You got some popcorn lovers. Want to determine if it is better to use the popcorn button on the microwave oven. Don't do that, by the way. Or use the amount of time recommended on the bag of popcorn. Always stand by the popcorn where the microwave is going. Trust me, I've done way more damage than you want to know. To measure how well each method works, they will count the number of unpopped kernels remaining after popping. To obtain the experimental units, they buy 10 bags, each of 4 different varieties of microwave popcorn. And we have butter, cheese, natural, and kettle. Now we want to describe a randomized block design for this experiment. Now think about it. We got 4 different types of popcorn. They all have their own thing going for them. Some might produce more popcorn kernels than others. So we might think it's best to block these by the type, right? The varieties. So what I'm going to say here is form blocks based on variety of kernels. We think they might differ by the variety. Place all 10 bags of each variety in their own containers. So have 4 separate containers, mix them well, randomly select 5 without replacement, get them the popcorn button, and then the other 5 will get the instructions, just going by the time. Do the same thing with the other containers. So every different container of the varieties will do their own little completely randomized designs. Then after all the bags are popped randomly, count the number of kernels in each bag. Then you can compare the results within each variety, and then you have what's called a randomized block design. Why would a randomized block design be more preferable here? Well, it accounts for variability in the number of unpopped kernels created by the different varieties of popcorn. So it makes it easier to determine if using the popcorn button is more effective for reducing the number of unpopped kernels. In other words, if you randomly assigned, let's say we have 40, we got 40 bags of popcorn and you just kind of mix them all up. If you randomly assign 20 to the popcorn button and the other 20 to the time, then it is possible that you have a majority of those one group that might only have butter and cheese, and maybe those produce more kernels than the natural kettle, or vice versa. So we want to make sure we separate them so that we can measure within each one. All right, so that brings us to another type of specialized blocking called a matched pairs. And in which this case here, a lot of times this is each individual is so unique that it's best to maybe separate each one person and give that person or experimental unit both treatments randomly assigned. Or if you have two similar people, group them up by pairs, and then one of those persons in the pair gets one of the treatments randomly assigned, the other gets the other, and then compare within each pair, and then group them together after that. That's called a matched pairs design. So there's kind of two approaches. Each individual subject could be its own block, or two similar subjects could be their own blocks. Matched pair is a type of blocking. So you could either do it by pairs or by each person getting both treatments. Not every matched pair can be done where every person can get both treatments. So you have to decide that based on the type of experiment you're doing. Here's an example. A consumer organization wants to know if using a certain fuel additive increases the fuel efficiency in miles per gallon of cars. A total of 20 cars of different types are available for testing. Design an experiment that uses a matched pairs design to investigate this question. Explain your method of pairing and how you'll randomly assign the treatments. Now, in this problem here, every car is kind of different. You know, you pick 20 random cars on the road, chances are they're all going to have different fuel economies. So give each car both treatments in random order. In other words, use that fuel efficiency. I think we're doing a fuel additive. And we're going to randomly assign whether they get the fuel additive or not. And then let them measure the fuel efficiency. And then after they have a new tank of gas, they'll get the other treatment without the fuel additive and compare the miles per gallons within each car. So for each car, flip a coin. Heads will get the additive first and no additive second. We want to randomly assign that. Tails will get the no additive first and additive second. For each car, record the fuel efficiency after using each treatment. Compare the fuel efficiency with and without the additive for the 20 cars. That'll give you better results that way. So let's do a little check your understanding. Researchers would like to design an experiment to compare the effectiveness of 3 different advertisements for a new television series featuring the works of Jane Austen. There are 300 volunteers available for the experiment. Describe a completely randomized design to compare the effectiveness of the 3 advertisements. So what we can do here is just number them all 1 to 300. Everybody's in a pot with a completely randomized design. Use a random number generator to select 100 different volunteers to show the first ad. Do the same thing with the next ad. Select 100 different numbers randomly. Those get ad number 2. And the remaining 100 will get the third ad, measure their responses, and compare the results. Easy breezy. Now, let's look at a different type of experiment. A randomized block design. How can we do that? And this can be up to your interpretation. How might different people react to advertisements for a new television series featuring the works of Jane Austen? I'm not familiar with Jane Austen, so I don't know how I would be impacted on that. Some people that might be familiar with Jane Austen may have a better understanding of how this would affect them, or if their interest level would be piqued for these ads. So you could group them by their familiarity with the works of Jane Austen. You'll have 2 blocks in that case. Both blocks, whether they know or do not know Jane Austen, would repeat the experiment from part A, where a third of each group would be randomly assigned to each of the ads. Measure the responses, compare the results within the blocks. So that's a simple way to do it. Why would that be preferable? We think maybe a randomized block design accounts for the variability and effectiveness. That's due to the subject's familiarity with the works of Jane Austen. This makes it easier to determine the effectiveness of the 3 ads. How else could you have blocked them? You could have think of different ways to do it than by that. Maybe you could have done it by sex. Maybe you could have done it by age. There's a lot of different ways you can think about how to group people up that might react similarly to different treatments. So this is just one example. All right, here's another activity. This is going back to the matched pairs activity. So we're going to go back to the caffeine, except this time we have a little twist, okay? So this time I want to show that maybe everybody reacts differently to caffeine. I know I drink coffee every day, so giving me a small cup of cola might not do a whole lot for me for my pulse rate. So what I want to do is maybe split everybody up by their own individual block. We're going to do one experiment at the beginning where we're going to, one day, we're going to take these 20 people and we're going to randomly assign them either cola with caffeine or cola without caffeine. But we're not going to average the groups entirely. What we're going to do is we're going to measure those results. And then on another completely day after the caffeine has worn off, and making sure they come to school in a similar way they came to school the previous time, they're going to get the other treatment. So if they got the caffeine first, they're going to not get it second. And then if they got the caffeine if they got the no caffeine first, they're going to get the caffeine second. Here's some results from that. Okay, so if you look at the subjects, each of these letters are the 20 subjects, and these numbers represent the difference in pulse rates, final minus initial, for the caffeine versus the no caffeine. And we basically subtract these within them, and you get all these mean differences down here. And if you get the average of them, it ended up being 2.35, which is a little bit higher than prior to. Now, this may indicate that caffeine actually does have an effect on pulse rate. So we can simulate this, and if you go to this bit.ly CAFSIM part 2, you can follow the spreadsheet. It's very similar to the last one, but there's a little bit more steps. I'm not going to do that here. So you can do that on your own, but what you're going to want to do here is think about making a simulation with your class if you're a teacher, or if you're in the classes, maybe compile this data with your students. Now, I had to do a lot of data points for this, okay? I had to do a lot of simulations of the simulated mean differences. And so there's 1,000 plot points here. And we want to know, do we have statistically significant results? So let's think about where 2.35 lies, because that was what our difference was here. And out of all these, assuming that there is no difference, I'm only getting one out of these 1,000 that even give me a number 2.35 or higher. So that's a pretty small percentage. So what I would say in this, the context of this problem is, since only 1 out of 1,000 simulated differences had a difference of 2.35 or more, we actually do have convincing evidence that caffeine affects pulse rates, assuming that it doesn't. So because that likelihood is very small to occur by chance alone, the results of our simulated experiment are indeed statistically significant. So it turns out doing a match pairs activity and grouping people up by how they individually react to caffeine and compare within did produce statistically significant results, whereas just doing a completely randomized design like before didn't quite work in that case. So you can see how that would be a benefit here. Lastly, let's talk about something called the scope of inference. That's just something we've already talked about before. If we do a randomly select from a population, we can make inference about the population we select from. If we do random assignment, we can show cause and effect if we have statistically significant results. So here's like a little two-way table here that kind of explains that. All right, last example and a follow-up question after that, and we'll be done with this video. Thank you for watching, by the way. Researchers at the University of North Carolina were concerned about the increasing dropout rate in the state's high schools, especially for low-income students. Surveys of recent dropouts revealed that many of these students had started to lose interest during middle school. They said that they saw little connection between what they were studying in school and their future plans. To change this perception, researchers developed a program called Career Start. The central idea of the program is that teachers show students how the topics they're learning about can be applied to specific careers. To test the effectiveness of Career Start, the researchers recruited 14 middle schools in Forsyth County to participate in an experiment. 7 of the schools, determined at random, used Career Start along with the district's standard curriculum. The other 7 schools just followed the standard curriculum. Researchers followed both groups of students for several years, collecting data on students' attendance, behavior, standardized test scores, level of engagement in school, and whether or not the students graduated from high school. There's a lot of variables in that. Results. Students at schools that use Career Start had statistically significant better attendance and fewer discipline problems, earned higher test scores, reported greater engagement in their classes, and were more likely to graduate. Here's the question. Is it reasonable to make a cause and effect conclusion based on the study? Explain your answer. Well, both treatments were randomly assigned, so the results were statistically significant. Therefore, we have convincing evidence, and since there is convincing evidence that this curriculum caused better attendance, it is reasonable to assume that. So I should probably say yes here, it is reasonable. Okay, there is convincing evidence. How about part B? What is the largest population to which we can generalize the results of the study? Now, in order to generalize to a population, we have to think about, did we randomly sample? And we did some surveys here. Researchers were concerned about the increased dropout rate. If we look over here, they recruited 14 middle schools in Forsyth County to participate in the experiment. The schools were determined at random, used Career Start along with the district standard curriculum. The other 7 schools followed the standard curriculum. It looks like they weren't randomly selected from a population, because we're talking about specifically 14 middle schools were recruited, not randomly selected. So because of that word recruited, we can only apply it to the schools similar to those in the 14 schools that were recruited in Forsyth County. We can't go to a larger generalization than that. All right, let's look at this last check your understanding. You can pause it, try it on your own if you'd like. When an athlete suffers a sports-related concussion, does it help to remove the athlete from play immediately? Researchers recruited 95 athletes seeking care for a sports-related concussion at a medical clinic and followed their progress during recovery. Researchers found statistically significant evidence that athletes who were removed from play immediately recovered more quickly, on average, than athletes who continued to play. Is it reasonable to make a cause and effect conclusion based on the study? Explain your answer. Well, we did not do the holy grail of an experiment, and we did not randomly assign, did we? In fact, if you look at the question, it says it's an observational study. So how do we know it's an observational study? Well, what happened was we recruited 95 athletes seeking care that were already there. Okay, we didn't ask them to get injured, so we can't really assign that. So we can't really make a cause and effect here. Now, we can still say a relationship. We just can't say that this caused that. Let's look at part 2. What is the largest population to which we can generalize the results of the study? Well, again, they were not randomly selected. They were recruited, so the results can only be applied to athletes like the one in the study. All right, guys, that wraps up this lesson. Let's do a little quick summary. First thing is just know the types of experimental designs. From our last lesson, we have completely randomized design. And now we learned about 2 blocking designs, a randomized block design and a matched pairs. Statistically significant just means that when you have an observed difference in responses between groups that's so large that it is unlikely, and we typically say less than 5%, to be explained by chance variation in the random assignment, we say that's statistically significant. Finally, the scope of inference just allows you to apply your results. So if you randomly select, you can make inference about the population you select from. If you randomly assign, you can make inferences about the cause and effect of a treatment. And that wraps up this lesson. Thank you for watching, guys. I appreciate your support.